Hello, ladies and gentlemen. It's my pleasure to welcome every one of you to the second part of our introduction to matrix algebra. If you have been following us, we started by looking at the definition of matrix algebra, types of matrix algebra, matrix operations. We consider addition and subtraction of matrices, scalar multiplication, and several other things. So today we want to continue, and we shall start with matrix multiplication. So let me share the PowerPoints. So let me share the PowerPoints. Okay. Yeah. Beautiful. So we go straight to matrix multiplication. Yeah, we stop at scalar multiplication, so matrix multiplication. So when you are dealing with matrix multiplication, the most important thing, or maybe I should say the first thing you have to take into consideration is the dimension of the matrices that you want to multiply. For instance, here we have A to B. This is 3 by 2, and our B is 2 by 2. For conformability for multiplication, you have to consider the role of the column of the first and the role of the second. So here we have the column of A to be 2 and the row of B to be 2. So these two must be the same. If they are not, then they are not conformable for multiplication. And the product will always lead to the row of the first and the column of the second. So in this case, if we multiply our AB, the result must be 3 by 2. Just what we have here. And in the process of multiplying, in this case, it is the row by the column. The row by the column. Take, for instance, if you look at the first row, we have -1, 3. So we have to multiply this -1 by this -3 and add it to the multiplication of this 3 by this -4. This is what we have here. And that is how we obtain this -9. For the second column, you do the same. This -1 and this 2, you can see, this 3 and 1. And that is how we obtain this one. Then you follow the procedure. This 4 minus 2 minus 3, 4. 4 minus 2, 2, 1. 5, 0, minus 3, 4. 5, 0, 2, 1. You can see that is what is illustrated here. Let's consider a typical example again. Let's say we have our A to be 2, 1. This is 2 row by 1 column, 2 by 1. And we have our B to be 4, 5, 6, 7. And that is 1 row by 4 columns, 1 by 4. If you look at this, we have 1, 1, which means they are conformable for multiplication. And the result will be 2 by 4. I want you to try it on your own. But there is one thing I want you to consider. For this, our example, AB. Now we know that AB is possible because the column of A is the same as the row of B. But is that true? Can we say the same for BA? For BA, for instance, our B is 2 by 2. Our A is 3 by 2. So we say BA is not conformable for multiplication. So unlike when we're considering integers, when we can say at all times that our AD is equal to BA, for matrices, AD may not be equal to BA. Take note of that. So that's, you must always remember the conformability rule. That is always a very good starting point anytime you want to handle matrix multiplication. So I say that again, conformability rule is very, very important. And you have to ensure that you take conformability rule into consideration before you proceed in the multiplication of matrices. That's very, 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 very important. Take notes. So what are the basic properties of matrix operations now that we've gone through matrix addition, subtraction, and we've gone through scalar multiplication and multiplication of matrices. The first property is A plus B is equal to B plus A. That's cumulative property, that is, you add it together. And this also is true when you are considering integers too. So A plus B is equal to B plus A. So let's say our A is equal to 1, 3. Let me do it. Better. So let me pick another example. So let's say my A is equal to 1, 2, 3, 4. And my B is equal to 3, 4, 5, 6. So my A plus B give me what? This is 4, 8, 6, 10. And my B plus A will give me the same thing. So irrespective of the dimension, even if you have 100 by 100 square matrix. Then we have this associative rule for addition. So we state that sorry, let me clean this very well. So we state that A plus B plus C is equal to A plus B plus C. So let us have another, let's say we have our C equals to 4401. So our A plus B plus C will be 1, 3, 2, 4. Plus, let us add B and C. That would be 7, 9, 4, 7. So, and that will give us what? 8, 12, 6, 11. Beautiful. So now our A plus B is 4, 8, 6, 10. So add it to C as 8, 12, 6, 11. You can see. So this is what we're saying. And just practice some of these things by yourself. If you multiply any matrix by identity matrix, it's going to give you that matrix. So it's just like when we're multiplying our numbers by 1 when we are dealing with integers. So this is what we are saying here. So let us look at it. So let's consider. Let's pick an example to illustrate what I'm trying to say here. So let's say I have my A equals to 2, 1, 0, 1. And you know, my identity matrix with respect to 2 by 2 matrix will be 1, 0, 0, 1. So okay, let me put it here. So 1, 0, 0. So let us multiply. So the product will give us. So this is 2 multiplied by 1, which is 2, plus 1 multiplied by 0. That will give us 0. That's 2. And here we have 2 multiplied by 0, which is 0. 1 multiplied by 1 will give us 1. And this is 0 multiplied by 1, which is 0, plus 1 multiplied by 0, that will give us 0. And this will give us 0 plus 1 multiplied by 1. You can see it's equivalent to our original matrix. So when you multiply any matrix by identity matrix, you're 100% sure that the result will be the original matrix. That's super straightforward. And let's look at another rule guiding multiplication. If you multiply the addition of a matrix by a scalar, so let's say I have I have C into A plus B. It's as good as multiplying C by A and adding it with multiplication of B by C. So let's say, for instance, let's say our seed is 3. Let's say 3 into, okay, let us define 2 matrices. A is equal to 2, 4, 1, 1. And B is equal to 1, 1, 3, 4. 3 into our A plus B, this will give us 3, 4, 5, 5. Yeah. And this will give us 9, 12, 15, 15. CA, that's 3 multiplied by, that's 3A. So 3A will give us 6, 3, 12, 3. And 3B will give us 3, 9, 3, 12. Okay, add together 3A plus 3B. You get this back. 9, 12, 15, 15. Yeah. This is the same as what we have here. So you can try it with several other examples, and you will see that that condition exists. So it's a property that stands in the dimension of the matrices that we're trying to multiply together. Then the last one we want to do, I want to point out, is this number 6. Let's say you have 2 constants, C and D. You add them together, and the addition, you multiply the addition by matrix A. It's as good as multiplying A by C and adding it with the product of D and A. We'll quickly illustrate that. So let's illustrate that with this matrix B. So let's pick our C. Let's pick our C to be 2 and our D to be 3. So C plus D will give us 5. So 5, 1, 3, 1, 4, that is 5 multiplied by B, will give us 5, 15, 5, 15, 5, 20. It's very clear. And now let us try to multiply B by 2. That would be 2, 6, 2, 8, plus multiply it by 3. That would be 3, 9, 3, 12. And if you add it together again, you get your 5, 15, 5, 20. Compared to this, same thing. So this is what we are saying. So I think it's very straightforward. Don't forget, these are some basic addition and scalar multiplication. So please take notes. Don't forget that AB, unlike when you go to B, and that's important points to take note of. Now, you know, in integer, we have division, but in this case, we don't call it division. Where we talk in terms of the inverse of a matrix. If there exists a matrix, be a member of M, is a kind of M by N matrix, such that you multiply A and B, you get BA, and the product gives you identity matrix. Then you can conveniently say that B is the inverse of A. A matrix that do not have an inverse is called non-invertible or singular matrix. Non-invertible or singular matrix. So in essence, just like what I said, if you multiply a matrix with the inverse, definitely you will get an identity matrix. But before we go into details of how to compute inverse of the matrix, we need to understand a term that is determinants. Determinants. The determinant of a matrix is a single numerical value, which is used when calculating the inverse, or when solving system of linear equations. So very, very important. It's always the starting point when we are dealing with the process of getting inverse of a matrix. For a 2 by 2 matrix, A11, A12, A21, A22, the determinants are usually represented by this symbol is equal to this A11 multiplied by A22. Then you subtract the product of A12 and A21 from it. So given A 10, 8, 8, 5, find the determinants. So the determinant will be 10 multiplied by 5. This cannot be 0. So the determinants, I have my A equals to 10, 8, 8, 5. So 10 multiplied by 5, 50 minus 64. So this will be minus 14. That is the determinant. That's how to obtain it. For a 2 by 2 matrix is super straightforward. But it's not all that straightforward when we are dealing with 3 by 3 or higher order matrices. So let's move to how to evaluate third order determinants. And I want us to pay attention, please. It's very, 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 very important. So evaluating third order determinants. So giving A as A11, A12, A13, A21, A22, A23, A31, A32, A33. If you want to calculate the determinants, if you want to get the determinants, you will have to obtain the minor of any row or column that you wish to use to expand it. Let me take it slowly so that you get it. Let's say I want to use this first row A11, A12. This row. I want to use this one. So I will take the minor. The minor is when I cancel the row and the column. What is left? If I cancel the row and the column, in respect of A11, what I'm left with is A22, A23, A32, A33. And that's how we obtain this. For A12, if you remove the row and the column, I'm left with A12, A23, A13, A33. For A13, I will be left with A12, A22, A13, A32. So usually, when we evaluate by means of lower order determinants, the process is called Laplace expansion. Laplace expansion. Laplace expansion. So I think the best thing here is to work with an example from beginning to the end so that we understand the process. And how come this negative? Because these are things that at times look confusing, although by the time I take us through the process of getting matrix inversion, it will become clearer and clearer. But let us, maybe we just look at this example, and we can even stop the class after dealing with this rule of determinant, because it's very, very important that you are able to solve for determinants. That's very important, because if your determinant is equal to 0, it's a sign that you cannot obtain the inverse anyway. So we'll soon get to that place. So given your A to be 2, 1, 2, 1, 3, 4, 5, 6, 7, 8, 9. Yeah, that's the have it. Yeah. Let us use the first row for our Laplace expansion. That is what is called cofactor, but don't worry, you will soon get to it later. It is a signed minor, but for you to understand the sign, for now, let us use a rule of thumb. Start with plus here. And, you know, usually we have negative and positive. So, and positive must not follow positive, and negative must not follow, negative must not follow negative. And the first one here must be positive. So this would be minus, this would be plus, this would be minus, this would be plus, this would be minus, this would be plus, this would be minus, this would be plus. So depending on your interest expansion. But let's say we want to use this first row. So the determinant of A will be, don't forget, this is plus, so that would be 2. into, if you remove the column and the row, if you remove the row and the column, here you have 5, you have 6, you have 5, you have 6, you have 8, you have 9. Since this is plus, I told you this will be minus. So that's how we get that minus. Don't forget this is 1. 1 into, so remove the row and the column, just, we are left with 4, 6, 7, 9. Then the last one, that's positive 3, that will be plus 3. So plus 3, so we are left with 4, 5, 7, 8. So the determinant here will give us, this is 2 into, this is 5 multiplied by 9. Yes, that will be 45. Minus 6 multiplied by 8, that will give us 48. Then minus 4 multiplied by 9, that will give us 36. 6 multiplied by 7, that will give us 42. Then plus 3 into 4 multiplied by 8, that will give us 32 minus 35. So the first one, don't forget, let me remove that too. So this is 2 into minus 3 minus minus 6 then plus 3 into minus 3. So this is minus 6 plus 6 minus 6. So which is equivalent to minus 6. So the determinant is minus 6. So I hope it is very, very clear indeed. So I want you to try as many examples as possible. You know, the beauty of learning matrices is that you can set example for yourself and just practice. So yeah, because like I used to say, anything mathematical, it's always good to allow you to do a lot of practices to end the class. So hopefully we'll continue from there. So in the next class, we'll be looking at matrix inversion. Then we'll be considering Cramer's rule. And if we can still extend it a little bit, then we look at the application, because the application is always the last aspect of the class. So once again, thank you for being part of this class.